All right, now let's just summarize some of the basic ideas we discussed in part 3 and then expand on our understanding of energy and forces. Previously, I emphasized that the history of science is a history of unifying ideas, and then we went straight to the core of what the history of physics is really all about. At every major milestone in our understanding of the universe, scientists found that things previously thought to be separate and unrelated were in fact just ways of experiencing a deeper truth. We saw how Otto von Guerich's discovery of the vacuum inspired the study of how temperature and pressure affects gases, liquids, and solids, and made it possible for us to imagine how objects move in the absence of wind resistance. It was once believed, for example, that heavier objects fall faster than lighter objects, which is true until you take wind resistance into consideration. Here we see a feather and bowling ball dropped simultaneously in a vacuum chamber. Ordinarily, the ball would fall much faster against wind resistance, but the absence of wind resistance makes it easier for us to understand how Newton arrived at his laws of motion. It was in fact Galileo who established the rate of acceleration for falling objects. We would later find that that rate is specific to earthbound objects. On the Moon or Mars, that rate of descent for free-falling objects would be different. The earliest philosophers were astute observers of nature, but they had not yet developed the sophisticated mathematical and experimental methods that would be coming along by the 17th century, where there was a greater emphasis on experimentation than intellectual speculation. It was only around this time that there emerged a highly disciplined community of scientists working to overcome their mutual distrust and establish standards for reviewing one another's work. Even towards the end of the 17th century, when Newton's Principia took the European world by storm, there was a controversy between Newton and Gottfried Wilhelm Leibniz over who had first developed the calculus as a complete mathematical system for characterizing change and motion. At that time, there was no actual name for what we today call the calculus. Newton himself called it fluxions, but a few years later, Leibniz would actually publish the first formal textbook on calculus and present it in the form which is now most familiar to mathematicians. The rivalry between these two giants of the age was a bitter one, but most historians today understand that the calculus was a mathematical system that had undergone many centuries of development with many contributors, beginning with what was known as the method of exhaustion, and that it was during the late 17th century that the time had come for it to mature into a complete system. Both Newton and Leibniz had made their accomplishments independently, and with the help of other mathematicians of their age. Isaac Newton's accomplishment, however, was the application of calculus to explain both the fall of an apple and the orbits of the planets in one complete language. This was an astonishing grand unification of what had previously been thought to be two completely different realms with each their own laws. This was during a time when simply traveling across the ocean was considered discovering a new world, and the heavens were just some mysterious parallel universe, thought to be forever beyond human knowledge. For people living during this period, Newton had opened the door to a parallel universe. People ignorant of that history, even today, fall into the trap of thinking about parallel universes instead of realizing that the history of science is, and always has been, a history of unifying ideas in tandem with the development of innovative mathematical ideas. Shortly after Newton, Antoine Lavoisier realized that for the universe to be understood by way of the development of abstract mathematical systems necessarily means that the universe must be thought of as a closed system. This is because mathematical equations are themselves closed systems. Any equation you can imagine in any mathematical system you can imagine can be placed to the power of 0 to get the number 1 as the answer. This is because abstract mathematical equations and expressions are the purest form of closed systems. To prove this point, Lavoisier would be one of the first people to establish the finest laboratory instruments for taking extraordinarily fine measurements to show that the total mass of a substance at one point in an experiment was perfectly preserved, though transformed, at the other end of the experiment. In other words, despite the fact that matter can take many forms, the total mass can never be created nor destroyed, only transformed from one state to another. In one fell swoop, Antoine Lavoisier would establish the first law of conservation of mass and become the father of modern chemistry. This understanding would not include energy for another 150 years. So today we have the first law of conservation of mass and energy. Now, the thing to keep in mind here is that perfectly closed systems exist only in mathematics and the universe itself as a whole. If the universe is not a perfectly closed system, then we have no reason to believe that mathematics can be a language for understanding the universe, and should have as much success in life relying on wishes, mysticism, and magic. The past several centuries of technological innovation pretty much speaks for itself on this point. We trust our technologies without question much more than we do mere chance, even if we don't always understand exactly how the technologies work. In any case, in the keeping of the unification of ideas, energy would of course be included about another 150 years later into the first law of conservation of mass and energy, and would even be more so by the time Einstein presented what is now his most famous mathematical equation. Prior to this, energy was actually thought to be a separate and invisible phantom substance that migrated in and among material things. There was the debunked notion that a substance known as phlogistan existed inside combustible substances to cause combustion. Though invisible, it could be detected as heat. People have long thought of energy as a substance in itself separate from matter, and it took a long time to dispel this understanding in our conventional wisdom. It was actually Daniel Bernoulli's hydrodynamica in 1738 that led to the kinetic theory of gases and showed that what we perceive as heat is in fact the motion of atoms and molecules. Energy is nothing more than the ability to do work. But this definition begs us to be more specific about defining work. And that is where we will begin in Part 5 as we continue our discussion on energy and forces.